Let's cover another property that the tree as a graph has. So this is theorem 50.5. Says that if we let G be a graph, then G is a tree if and only if every edge of G is a cut edge. G is a tree if and only if every edge of G is a cut edge. Remember that a cut edge is an edge that when you remove it, increases the number of components of a graph. Now, since a tree is connected, and if you remove a cut edge, you're going to increase the number. That means the resulting graph that you get when you remove an edge from a tree is a disconnected graph. So I'm going to use that to make my proof. So let's go in the forward direction. This is an if and only if proof, so we have to do both directions. So the forward direction, we're going to assume that G is a tree, and we're going to let E be an edge of the graph. So what we want to show is that because it's a tree, E has to be a cut edge. Now, to be a cut edge, we basically want to show that G minus E, that is the graph when you remove E from it, is disconnected. So let's let E be the edge XY, which means there is an XY path in G, namely that single edge XY, right? So if X and Y are both vertices of G, then there is an edge from X to Y because it's connected. We're picking the edge XY, just a single edge. By the previous theorem, there is a unique path from X to Y. If XY is that path, that edge XY is that path, then it's unique. That's the only one. So if I remove that is delete XY, then there is no XY path in G minus E, which means G minus E must be disconnected. You have two vertices in G minus E that are no longer connected, which means E is a cut edge. Done. So let's go back the other direction, and we're going to suppose that every edge of a graph G is a cut edge, and we want to prove that that means that G has to be a tree. So suppose that every edge of G is a cut edge. We want to show that G is a tree. In particular, we want to show that it's acyclic. Assume, for the sake of a contradiction, that G contains a cycle. Since a tree is acyclic, then we're going to assume that it's not acyclic, that it has a cycle, and show that leads to a contradiction. Let E be an edge of the graph. We'll call it XY, and it's going to be an edge of that cycle, C, that is in G. Since E is a cut edge, let me draw this for us. X and Y, there's the cycle C. We'll call that edge right there E. So one edge of the cycle. Now, since E is a cut edge, then G minus E is disconnected. If you remove it, it's no longer connected. So if it's disconnected, we're going to let A and B be two vertices for which there is no path in G minus E. So let A and B be in two different components of G minus E. So there is no path from A to B. Now we're going to prove that I can actually form a path from A to B that's still in G minus E, and that's then the contradiction. If it's disconnected, then there can't be a path, right? There are 2 points for which there is no path. So in G, we know that there is a path from A to B. There is an A-B path. We're going to call it Q because G is connected. So from A to B, there is a path that follows along E, and whenever you remove E, there's no longer a path. Except because E is part of this cycle, there actually is, and that's going to lead to the contradiction. So let's let Q go from A all the way to X, and then from X to Y, and then all the way to B. And let's let P be the path that's from X to A along the cycle C, that is, starts here and goes around this way and ends up at Y. Now, because I can follow from A up to X and then around P and then from Y all the way to B, even when I remove E, that means there is an AB path in G minus E. If I follow Q from A to X, and then X to Y along P, and then Y to B along Q, then there is a path from A to B in G minus E, but we just said that there is no path in G minus E, and so we have a contradiction, which means G must be acyclic. The only thing we assumed is that there was a cycle, but assuming there's a cycle leads to the fact that we have a contradiction, so G is acyclic. Thus, G is a tree. Thus, we've proved the property that if it's a tree, every edge is a cut edge. If every edge is a cut edge, then it's a tree.